Hey everybody, in this video we'll be talking about amines. Amines are functional groups that contain nitrogen atoms. A primary amine is where the nitrogen atom is connected to one carbon atom and two other hydrogen atoms. A secondary amine is when the nitrogen atom is bonded to two carbon atoms and one hydrogen atom. A tertiary amine is when the nitrogen atom is connected to three carbons and, more importantly, no hydrogen atoms at all. The nitrogen atom in an amine functional group occupies a trigonal pyramidal shape, where the three bonds are subtended at an angle of 106.7 degrees away from the electron lone pair of the nitrogen atom. It is important to note that this is a different structure and shape to trigonal planar, as the electron lone pair repels the covalent bonds, preventing a trigonal planar shape from forming. The names of amines are denoted by the amine suffix. This is best demonstrated in a primary amine, such as propan-1-amine or 1-propanamine. In secondary tertiary amines, the names have to account for the additional hydrocarbon chain that is attached to the nitrogen atom. The position of this hydrocarbon chain is denoted by the letter N. For example, in this secondary amine, the main functional group is an ethanamine, as there are two carbon atoms connected to the nitrogen. The remaining carbon atom becomes a methyl group. Therefore, the name of this secondary amine is N-methylethanamine. In this tertiary amine, the longest consecutive carbon chain is just one carbon, no matter where you count it from. So the main amine functional group is methanamine. This leaves behind two methyl groups attached to the nitrogen atom. Thus, the name of this amine is NN-dimethyl-methanamine. Amines have relatively low priority in the nomenclature, lower than alcohols but higher than hydrocarbons. In molecules where there's another functional group with higher priority, such as a carboxylic acid, it is denoted by the amino prefix. For example, the name of this molecule is 2-amino, where the amine functional group is positioned on the second carbon atom, ethanoic acid, referring to the main high priority functional group that is the carboxylic acid. The most important property of amines is its basic nature. Amines are Bronsted-Lowry bases, as the nitrogen atom with a lone electron pair has the ability to accept protons. All amines are weak bases, so they're partially ionized in water. After an amine molecule gains the proton from water, it forms a conjugate acid that contains a positively charged nitrogen atom, while the water molecule, after giving away the proton, produces a hydroxide ion. Since amines are weak bases, their ionization reaction is reversible, as you can see here, and this reversible reaction usually exists in an equilibrium if the conditions allow it. Since amines are basic, they can be easily identified from other functional groups using a red litmus paper test, whereby the red litmus paper turns blue when it's dipped in the basic solution. In addition, a pH probe can also be used, and of course this will give you a pH reading of greater than 7 at room temperature. Boiling and melting point of amines vary depending on the type of amine. Primary amines have relatively high boiling points, as they can form all three types of intermolecular forces: dispersion, dipole-dipole forces, and, more importantly, hydrogen bonds. As seen in the diagram, a molecule of primary amine can donate up to 2 hydrogen bonds, as it contains 2 hydrogen atoms bound to the nitrogen. In addition, it can also accept 1 hydrogen bond, as the nitrogen atom contains a lone pair of electrons that allows it to accept the bond. Since primary amines have 2 hydrogen atoms bonded to nitrogen, whereas secondary amines only contains 1 hydrogen bonded to nitrogen, primary amines can form more hydrogen bonds than secondary amines can. Therefore, primary amines have higher boiling points than corresponding secondary amines, that is, those with similar molecular mass. Secondary amines can also form 3 types of intermolecular forces: dispersion forces, dipole-dipole forces, and hydrogen bonds. Each secondary amine molecule can donate 1 hydrogen bond and also accept 1 hydrogen bond. While they have relatively high boiling points compared to other functional groups, They have lower boiling points than primary amines because they cannot form as many hydrogen bonds. The difference in boiling point between primary and secondary amines are further demonstrated here. Propan 1-amine, which is a primary amine, has the same molecular formula as its chain isomer, N-methylethanamine, which is a secondary amine. Since the molecular masses are the same, the strength of the dispersion forces should be similar. However, if you take a look at the table, you can see the boiling points between these two compounds are fairly different. The primary amine has a higher boiling point than the secondary amine because it can form more hydrogen bonds, as we discussed earlier. If you understand the differences in boiling point between a primary and a secondary alcohol, it shouldn't be difficult to recognize that tertiary amines have a much lower boiling point. This is because they cannot form hydrogen bonds, as the molecule of tertiary amine does not contain any hydrogen atoms bound to a nitrogen. If we go back to the example we used before and add a tertiary amine for comparison, we can see that the tertiary amine has a much lower boiling point compared to the secondary and the primary amine with a similar or identical molecular mass in this example. And just to clarify, the reason for this big difference is that tertiary amines cannot form hydrogen bonds as they do not contain hydrogen atoms bound to a nitrogen atom. Amines have higher boiling points than hydrocarbons because hydrocarbons are non-polar molecules that can only form dispersion forces. Primary and secondary amines have higher boiling point than ketone, aldehyde, and esters, as these three functional groups cannot form hydrogen bonds. I have specified primary and secondary here because tertiary amines have lower boiling point than ketone and aldehydes, as tertiary amines cannot form hydrogen bonds, and also they form weaker dipole-dipole forces compared to ketones and aldehydes. Boiling point of tertiary amines and esters are very difficult to predict, so you won't need to know this detail. All types of amines have lower boiling point than alcohols. This is because alcohol molecules can form stronger hydrogen bonds. The strength of a hydrogen bond is largely determined by the electronegativity of the atom that is attached next to the hydrogen atom. Since the oxygen atom in an alcohol is more electronegative than the nitrogen atom found in an amine, hydrogen bonds between alcohol molecules are much stronger than those between amine molecules. This is why primary and secondary amines have lower boiling points than alcohols do. Furthermore, tertiary amines have significantly lower boiling point than alcohols, as this group of molecules cannot form hydrogen bonds. Let's talk about solubility. In general, amines are relatively soluble. Primary amines are the most soluble amongst the different types of amines, as they can form the most number of hydrogen bonds. As you can see in this diagram here, each molecule of primary amine has 2 hydrogen atoms bound to a nitrogen, and each atom here can donate 1 hydrogen bond with the oxygen atom in water molecules. At the same time, the lone pair electron on a nitrogen atom can also receive or accept 1 additional hydrogen bond from the hydrogen atom from water. While secondary amines are still relatively soluble compared to most other functional groups, they are less soluble than primary amines. This is because secondary amines can only donate 1 hydrogen bond due to the presence of only 1 hydrogen atom bound to a nitrogen atom. They can also accept 1 hydrogen bond, as the lone pair electron on nitrogen can form the hydrogen bond with the hydrogen atom from the water molecule. Tertiary amines are the least soluble amongst the amines. They can accept 1 hydrogen bond from water due to the presence of the electron lone pair on the nitrogen atom. However, they cannot donate any hydrogen bonds, which is the reason why they are less soluble compared to primary and secondary amines. It is good to remind ourselves that small amines are soluble in water, and their solubilities decrease with increasing number of carbon atoms. This is because as the number of carbon atoms increases, the molecule becomes less polar. For example, 1 pentanamine is less soluble than ethanamine because it has more carbon atoms and has a reduced polarity.